Hello, and welcome to this series of videos that introduce the mathematics of signals. For a playlist with all the episodes in this series, please click the link at the top of the screen. In this part, we will introduce complex Fourier series. So a quick outline first. We're going to try and answer questions such as what changes to Fourier series, which we saw in part 4, are necessary to use the representation of real signals by complex numbers, as was introduced in part 6. And then we're going to ask what effect does this have on the spectra it computes. So the route we're going to take to this is to take Fourier series and add complex numbers. In part 4 of this series of videos we explored real valued Fourier series, and these showed that any real valued signal that is periodic with time period big T can be expressed as a weighted sum, that means a sum with coefficients, of real-time harmonic sine and cosine waves. So this is the equation we had here. So if you haven't seen this before, please go back to the part 4 video and find out more about it. But what we essentially have is our signal xt. We have a 0 Hz, or DC as we sometimes call it, term A0 over 2. And then we have a sum over these harmonic frequencies Fn. So n is the index, and Fn is defined on the right there. It's the index over the periods t, the repetition period. And then we have these cosine waves and sine waves at those frequencies. Of course, they'll be 90 degrees out of phase with one another, and they have their own coefficients an and bn. So as I've mentioned in some other lectures, using this an and bn for the cos and the sine separately is a different way of writing amplitude and phase. But in part 6 we saw that complex numbers were useful for describing both the amplitude and the phase of a time harmonic signal. So actually you can bundle that A and that B, or the amplitude and the phase that come from them, all into one complex number instead. So if we've got amplitude A times cos omega t plus phi, where phi is the phase, then you could say that that's the real part of some complex signal, C times e to the I omega t, where C is amplitude A times e to the I phi, which is the phase. And this e to the I whatever is this sort of complex exponential notation that we introduced in part 6. So again, if that's not familiar, then stop now and find that part 6 video and go and watch that, and then come back here and it will hopefully make some sense. And this is really useful because it allows amplitude and phase changes to be represented by multiplication as well. So a lot of systems, that's really useful. So the question is, can we combine those ideas, and why might we want to do this? So let's just deal with that last point first of all. And this is really about this idea that amplitude and phase changes can be represented by multiplication. So if we had a linear time invariant system, which is a kind of class of systems you could put a signal through that covers all sorts of systems that we might have in audio and acoustics, then what we find is that for any LTI system, pretty much regardless of what it is doing, if you put in a signal that is some complex amplitude times some complex exponential, then you'll get out another signal that's a complex amplitude times a complex exponential, and all that's changed is that you've got a different complex amplitude, which is really easily related. It's the input one times the transfer function h evaluated at the angular frequency omega that we're thinking about. So all the complexities that might happen inside the system turn into a simple multiplication by h evaluated at angular frequency omega. And this is called the transfer function. It changes the amplitude and the phase of the frequency components. So this is a really neat way of writing, and manipulating just what a complicated system might do. And this is just a really kind of elegant and easy way of dealing with these types of systems, which is why you see Fourier analysis used so much. And as well as holding for individual systems, it holds for sums of complex time harmonic signals too, i.e. complex valued Fourier series, which is what we're going to talk about now, which can represent, again, arbitrary periodic signals. And what's going to happen is that each frequency component, which you can think of separately. Remember, we had a summation of different frequencies in that Fourier series. Each of them is just going to be multiplied by its own h omega. So each one, you kind of take it apart into its frequency components, you multiply each one separately, you put it back together. And I had a little slide illustrating that at the end of the part 6 talk. And we can generalize how we write this and say that it also allows us to find output spectra y omega, so the spectra of y of t, from the input spectra x omega. So you might see things like this written as well, which could be thought of as applying to a Fourier series if you were looking at these spectra at lots of discrete frequencies, or when we come to Fourier transforms, we'll write these kind of continuous functions of omega or frequency like this. On that note, I might sometimes write frequency rather than omega with all these things. I'm just explaining exactly the same idea, but I'm making them functions of frequency in hertz rather than angular frequency in omega. But the general principle still applies. What the system does can be represented by multiplication by this transfer function, evaluated at the appropriate frequency. Right, so that is why this is going to be useful. So let's get on with working it out. So the process is to start with real Fourier series and work in some complexity. And in most of the previous talks on this, I'd worked quite hard to add as many images and animations and pictures as possibly can. We're really getting to a point now where that's quite difficult. I've got some animations later on illustrating some points, but for this I'm just going to have to go through and do the maths because there's no real easy way to draw pictures of it. But I know that some people watching this course might not be completely unfamiliar with the ideas, so just as a bit of a preamble, I'm just going to define a couple of things I'm going to use in a minute. So in part 6 we met Euler's formula, this rather strange equation, e to the I theta equals cos theta plus I sine theta. And as I explained then, this is kind of something you've just kind of got to get used to. It's a rather weird thing when you first see it. But it does work. I showed a proof with some Maclaurin series as to why that works, and we've already seen it proving useful. So you kind of just have to accept that this works in a way. And it follows the rules of standard mathematics in an easy to apply fashion. So I'm going to call that one equation 1. I'm then going to look at a version with theta negated. So I've got e to the minus I theta. And so the minus theta goes inside. I've got cos minus theta, I sine minus theta. Now cos is actually symmetrical, so I can just get rid of that minus from the theta and nothing happens. Sine, however, is anti-symmetric, it's got odd symmetry, so sine minus theta is minus sine theta, it's sine theta negated, so I can take that outside and it looks like that. And if I add these two functions, I'll find that the imaginary parts cancel, the real parts, the cosines, add, so I get 2 cos theta. And if I rearrange that, I get this classic formula for cos theta expressed in terms of complex exponentials. Similarly, if I subtract them, then the real parts cancel and the imaginary parts add, so I get 2i sine theta. And that can be rearranged to this other classic formula that gives you sine theta from complex exponentials. So let's take those, and we're going to use those in our Fourier series. Here we go. So if we look at this equation, the main building block is this term in the bracket inside the summation, an cos 2 pi fn theta plus bn sine 2 pi fn theta, not theta, t. So let's just take that out and have a look at it. Here it is. And we can use those two formulae we just derived to rewrite that in terms of complex exponentials. So if I just do that, we'll get this. All I've done is plug those formulae in with theta equals 2 pi fn t. And then what I can do is I can just gather the terms together. I've got some that have got positive exponents and some have got negative exponents. So I'll just gather those together and just put the coefficient in the bracket. So now I get an over 2 plus bn over 2i times this positive one with the positive exponent, e to the 2 pi fn t. And then I get another one, an over 2 minus bn 2i times 1 with the negative. And noting that fn is n over t, I can say, well, actually this negative one here is just fn evaluated with a negative n. So I can write this here as a sort of compact way of writing that. So my term on the left hasn't really changed. I've just defined an xn, which is going to equal the stuff in the bracket. And similar on the right hand side, but I'm calling this minus n because of the minus sign in the exponent, which I've kind of brought into fn and then sort of moved onto the subscript. So just to surmise how xn is defined, if n is greater than 0, we've got an minus ibn over 2. Now what I've done here is I've just brought the I out of the denominator from the left hand bracket up into the numerator, so it's ended up negated. If n equals 0, then I'm just covering the a0 over 2 term from the original Fourier series equation on the top left. And this works because, much like cos of 0 is 1, e to the I 0 is also 1. So this all just kind of works conveniently in the same framework. And then if n equals 0, so n is smaller than 0, as I was just saying on the second term, then we have an plus ibn over 2. So we can write this into another summation series here, and all those kind of terms from the Fourier series will get bundled into one thing. It's all rather nice and compact. But a couple of things have come up as a result of this. So we had a positive frequency here, e to the I 2 pi fnt. That was kind of what we were used to. And that's straightforward. But then we've got this other term turn up here with minus n, and that is best thought of as a negative frequency. I mean, if you see where that came from, it was e to the minus I 2 pi fnt. So this is actually a negative frequency. If you work out n over t for fn with minus n, it's obviously going to come out as negative hertz. So what on earth does that mean? So I'll talk about that in some subsequent slides. But the main difference that this makes is that n can actually now go down to the summation. Instead of going just from 1 to infinity, is now also including 0 and going to minus infinity to cover these negative frequencies. So, of course, in practice, you truncate this series and you truncate it in maximum and minimum values of n, whereas in the real Fourier series, you just truncated it in a maximum value of n. And the other thing we can see is that the xn are now complex. We've got an plus or minus ibn over 2. So we've got complex coefficients now as well. So let's take a look at how these xn are computed. So in our real valued Fourier series, we had these two integrals that allowed you to calculate the an and bn coefficients. It was the signal multiplied by either a cosine or a sine wave at the frequency of the harmonic in question, integrated over the time period, and then multiplied by 2 over t, the big time period. So let's see how that works out. So xn, I'll take the positive frequency for what it's worth, is an minus ibn over 2 if n's greater than 0. And if we just substitute in the definitions for an and bn, we can end up with these two things. And what's happened is the 2 over t has turned up into a 1 over t because it's been divided by 2, and the bn1 has got a minus I in front of it. And if you look at those terms, you can recognise that inside the first integral is a cosine, and then we've got minus I times a sine in the second integral, and they're both the same frequency, so we can use cos minus I sine to bring those together into an e to the I complex exponential form. And that's actually going to be a negative frequency. It's going to be the minus 2 pi fnt because it was minus I times sine. Remember the identities from the earlier preamble slide. So that is actually what we're going to get. And this is actually really useful. It actually turns out to work for n equals 0 as well. You've just got a0 xn is just going to be 1 over t times the average of xt there. It also works for the negative values as well, for n smaller than 0. So it works for all three. So actually, instead of having 3 tested integrals, we've now just got 1. But we can work this out directly as well. We don't have to go via real value Fourier series, and actually the manipulation's actually a little bit easier. So we start with this integral, rather like we did when looking at real valued Fourier series. So we've got the signal xt times the rest of the tested integral, but I've not said what it's equal to yet. And then what we're going to do is we're going to follow the same process. In for xt, we're going to substitute this summation expression, and I can move the summation and the coefficients xn outside of the integral because summation and integration are interchangeable, and xn is just a coefficient that doesn't depend on time, so it can come outside. And that leaves us with this little integral term here. Notice that I've used fm in the testing term rather than fn, just so we can look at all the possible frequencies fn in the signal and see which one the tested integral terms that pulls out. So we'll have a look at this integral, and if we work that out, we can kind of rearrange this a bit. We've just put in the definitions for fn, and we get this, where we get both terms are dependent on big T. So we pull out all the constant factors, and we can see that we've got an n minus m in there. And basically, in the same way that we saw with cosines and sine waves, if you have anything that oscillates a integer number of periods in t, it's going to be negative as often as it's positive, and when you take the mean of that, which is essentially what this integral is doing, you're just going to get 0. It's going to average to 0. So that's exactly what's going to happen here. Any time when m minus n is not equal to 0, that integral is going to equal nothing. So the only time you get anything is when they are 0, and e to the I 2 pi 0 is 1. Integrate that, you get t. So the result of this integral is just t if m equals n, and naught otherwise. And this is, again, another orthogonality relation, but rather than being for those sines and cosines, it's for this complex exponential. And again, this kind of follows because all these frequencies are harmonics of the repeat period t. That's why it works. And it kind of follows naturally, as you saw from the previous slide, from the cosine and sine relation. So they're all interrelated because they're all related by Eulers' formula. So this may come as no surprise. But you'll see that actually, in terms of doing the integrals and the number of them, it's actually quite a bit easier. So the point is that we can get that directly. If we put that back in, we'll get that this sort of sifts out tx of m. So if we just take the starting and end result on that middle line, go back to using n instead of m and divide by t, then we get the kind of the integral on the right hand side that finds xn from x of t. So this is actually a little bit more straightforward than the cosine and sine one, so long as you're comfortable with complex numbers and complex exponentials. So that's time for a summary. So on the left hand side we have what I was calling the reverse transform. It's the synthesis. It synthesizes signal xt from this set of complex coefficients fn. And then in the right hand box we have the forward transform, which I like to call the sort of analysis part of the Fourier transform, and that's the one that finds the amplitudes and phases of these frequency components xn from the signal xt. And as I've said before, you can relate it back to real Fourier series by relating the coefficients xn to an and bn, so that's going to prove a very useful thing to know, because often we might be thinking more often of what the amplitudes and phases might be, and this is going to be useful to have this relation. We see that the complex notation is actually more concise. We've got we've only got two statements now instead of 3 or 4, and they're both rather shorter. So this is kind of handy. But some other things have come up. We now have negative frequencies. We have fn with n smaller than 0. The coefficients xn are now complex. However, when xt is real, they are conjugate symmetric. So you can see that from the definitions of xn from an and bn actually, that when n is smaller than 0, the imaginary part is negated relative to when it's greater than 0. So the real part stays the same. So the magnitudes are the same, but the phase is flipped. They're complex conjugates of each other. And the other kind of peculiar thing, which we'll just look at again, we'll look at all these things in a second, but the reverse transform produces an xt that is real, even though all the terms in it are complex. So you put on all this complex stuff on the right hand side in the orange box. Xn's complex, e to the I pi 2 nft is complex, but somehow or other you get out something that's real. And this is something you see often when evaluating complex Fourier series, that if you thought you were going to get something real and you don't, then you probably made a mistake in how you coded something somewhere. So that's a useful check. Another thing just to mention here is that complex Fourier series can also represent complex signals, in which case you still have all the same machinery, but the coefficients are no longer conjugate symmetric. We won't think about that here, but there are other applications where that proves really, really useful. Okay, so let's try and think of it first of all about these 3 points. So the first one is, what are negative frequencies? So to understand this, you're going to go back to these diagrams rather like I've had before, with these little animations of these things going round and round. And the one on the left we've seen quite a few times now, e to the I omega t, let's use omega here again, is cos omega t plus I sine omega t. And if we let that run, we see the thing goes anti-clockwise, and we see that we're sketching out a cosine wave, sort of, albeit rotated 90 degrees in the bottom graph, and a sine wave in the imaginary part on the right hand side there, top right. If we then move to the other graph, which is very similar but the negative frequency, so we've got e to the minus I omega t here, or omega is positive and real, then moving that through the machinery we just saw at the start of in the little preamble, we'll see that this gives you cos omega t minus sine omega t. So what's it going to do? Well, it's going to rotate the other way. And what you can see by comparing these is if you only look at the real part, you won't see any difference. They look exactly the same. So actually a negative frequency and a positive frequency, from the purposes of looking at cosines, is exactly the same. You'll get exactly the same thing out. But the imaginary part is negated. It's a complex conjugate, so it's actually sketching out minus sine rather than plus sine. Now these things will become a little bit different when we think about different phase in a minute, but you can immediately see here that if you add these two things together, the cosine parts would sum and the imaginary parts would cancel because they're the same but opposite sign. So we're going to look at this a little bit more now. We have pairs of positive and negative frequency terms in the complex Fourier series, and they're complex conjugates. So they will be xn, positive n, with e to the 2 pi fnt, and then the corresponding version with negative n, x minus n, for e to the I 2 pi f minus nt. And we've already discussed that x for minus n is the complex conjugate of s for plus n when the signal xt is real. That kind of came from the definition from the real value Fourier series. And you can also see, as on the last slide, that actually the complex exponential is actually a complex conjugate as well. So e to the I 2 pi f minus nt is e to the minus I 2 pi fnt, because of the way fn is defined. And then because of the way that complex exponentials work, that means that actually it's a complex conjugate the whole thing, because only the I sine bit has been negated. So actually you can just complex conjugate the whole thing. And when you have two numbers that are multiplied together, they're complex conjugates, then the product is also a complex conjugate. So actually these whole pairs of statements at the top will be complex conjugates. The two signals of positive and negative frequencies that are complex will be complex conjugates. And we're asking why the sums of these pairs give a real signal. And what we'll see is that the real parts sum and the imaginary parts cancel, as I was alluding to on the last slide. And this holds for complex numbers in general. If you have a complex number z and you add on its complex conjugate, then what you get from the first z is real z plus imaginary part of z. And then from the second complex conjugate you get real, but then minus the imaginary part of z, because it's been conjugated, that imaginary part's had its sign flipped. And if you add those together, the imaginary parts cancel, the real parts sum, and you get 2 times the real part of z. Rearranging that, you can also say that real z is half of z plus z conjugate. And we'll actually see this with the signals that we end up dealing with. So if you started off with a kind of notation where you had amplitude A times cos omega t plus phi, and you were going to represent that as the sum of a positive and negative frequency x I omega t, I have to switch back to omega here, apologies, plus x conjugate of e to the I omega t. That works so long as x is half of a to the I omega t. So when we were doing things before and I was saying that a cos omega t plus phi was the real part of c e to the I omega t, then that is the same as this, but now we've got two terms instead of just the c, and instead of taking the real part, we're using both of them, but we have this complex conjugate relationship, and the x's have only got half the amplitude that the single c complex amplitude would have had. So it all works out quite nicely, but you find that the amplitudes are halved because we've got positive and negative ones. So let's just have a look at a few more examples. So first of all, let's see how they sum when you're actually using time domain versions. And for this, I'm going to go back to my kind of phasor plot on this Argand diagram where the thing is rotating around versus time. And I'm going to have e to the I omega t in the left-hand graph. I'm going to have e to the minus I omega t, so the negative frequency, in the right-hand graph. And I'm going to have the sum of the two. And as we saw before, these rotate in opposite directions. But the important thing is that they're kind of locked with one another, and the real parts are the same. The imaginary parts are always opposite. You can think of these pictures as being vertical mirror images of each other, and when you sum them together, the real parts add, the imaginary parts cancel, and you get something purely real bouncing up and down on the real axis there. If we introduced a non-zero starting phase and some potentially arbitrary amplitude x of n, then things look more like this. Now in this example I've still chosen an xm with a magnitude of 1, so the plots don't really look much different. The main difference is the starting position's going to be different. So you would have this thing, as we've seen before, where with the radius of the circle is now the magnitude of xn, and for the positive frequency, we've got this kind of forward anti-clockwise rotation by the phase of xn. For the negative frequency, we have that the magnitude's going to be the same. It's a complex, x minus n is a complex conjugate of xn. It's the same length, it has the same magnitude, but the phase has been negated. So x minus n phase is going to rotate the other way. It's going to rotate clockwise down below the real axis. And then if we sum the two of these things, we will get something with twice the amplitude, with amplitude 2xn, as I was kind of alluding to before. The phase of xn still comes in inside, but the amplitude gets doubled. So in this particular case that I've drawn, I've got xn is amplitude of 1 and has a phase of e to the I pi over 3. So a phase of pi over 3. So the negative version that is conjugated is the opposite phase, negated phase, but you put these together and we get 2 cos 2 pi fnt plus pi over 3. Phase comes in there. So let's just see that go. It's going to look much the same. It just had a different starting position. There's nothing really to look at. But we see that 2xn magnitude comes out on the right hand side of the magnitude of the resulting cosine. And again, they cancel to nothing. Things get more interesting if you consider a pair of signals. So we've got xn there again, just as before. That's the same values, nothing new there. But now let's have a look at y. So this has got a slightly different amplitude, a slightly different phase. Everything else kind of follows through in exactly the same way, just labelled y rather than x. And in these examples, I've made y have an magnitude of 1.2, so it's a little bit bigger, as you can see. And it's got a bit of extra phase advancement on it, so it's got an extra pi over 4. So x had pi over 3 and y has got pi over 3 plus pi over 4, so it's a little bit further round. And that rotation is again anti-clockwise for the positive frequencies and clockwise for the negative frequencies. And when we put those together, we'll find that the phase, of course, turns up inside the cosine and the magnitude gets doubled out the front. Now, that's the same sort of stuff. Where the things gets kind of really interesting is if we start to think about a transfer function related x and y. So if you imagine that y is x times h, then h becomes the difference between between x and y. So the difference between the black line and the blue line. So the phase of h will give a little advancement, give a phase rotation. The magnitude will give a scaling, and for the real case, it's 1.2 e to the pi 4. Remember that y had the phase of pi over 3 like x plus pi over 4, so h is the difference between them. And yn for this particular Fourier series frequency is the transfer function evaluated at that frequency. Remember that a transfer function is usually for a real system that's, doesn't know what signal you're going to fit into it. We talk about periodicity of signals. That's a property of the signal. You then pass it through the system. You could pass a different signal with a different periodicity through in a minute. H is a property of the system. You evaluate it for a certain frequency. So that's why I've written it like this. But we can see that it's passed through by multiplication, as I was saying towards the start of this talk. Secondly, for the negative frequencies, we see exactly the same thing. Magnitude scale has the same effects. H is complex conjugated at this minus frequency. Let's just take a step back actually. What I'm saying here is that H needs to be complex conjugated at the minus frequency as well. So when you had a spectra, when you had the complex Fourier series, you would see that the coefficients are complex conjugates, but for a transfer function, we'll see that holds as well. So what the transfer function needs to do to the negative frequency is scale it in the same way and rotate it not in the same anti-clockwise direction, but now clockwise for the negative frequency, such that this symmetry kind of in the real axis vertically is maintained. So we actually need that H for the negative frequency is a complex conjugate of H for the positive frequency. So same magnitude, negated phase minus I pi over 4. And the same relationship by multiplication holds, but now evaluated for minus n. And putting these together into the final bit, we'll find that the magnitude that comes out, yn is the magnitude of h evaluated at fn for xn. Of course, the magnitudes are the same for both the positive and the negative frequencies. But the phases of the transfer function, like the other spectra, are negated and phases add. So the phase of y is the phase of h plus the phase of x, which is kind of what you saw in the previous definition for y. And just to see this animation go, this is kind of probably one of the last of these kind of hypnotic spinning animations you'll see in this little series of lectures, but it's one of my favourites because unlike some of the others where it's fairly obvious what was going to happen, you can look at this one and on the positive and the negative frequency, it's pretty obvious what's going on. These two things are kind of spinning around and you can kind of see that they have a symmetry about them if you keep an eye on them. They're vertically sort of mirror images of one another, and you can also sort of see that when you sum them they will give you zero imaginary part for that reason. But if you then look at the positive plus the negative part and how these two little blobs bouncing up and down are related to one another, you can kind of see the black one's chasing the blue one, but you would really struggle looking at that to write a mathematical relationship on how those are behaving relative to one another. It's difficult to make much out at all, whereas on the diagrams on the left, it's completely obvious that they're related by this fixed phase and fixed gain due to this transfer function. So this is a kind of nice example where you look at the time domain signal, you'd really struggle to know what's going on, but you look at the complex phases and you understand it a lot better. So to surmise, a complex version of Fourier series exists and is compact to write. There's only one term in the series, which uses complex exponential notation. And there's only one analysis integral, which exploits its own orthogonality property. It can also represent complex valued signals, though we won't do that. However, the coefficients xn are now complex. We now also have negative frequencies at fn with n smaller than 0. And if we have a real valued signal, we'll get conjugate symmetric coefficients x with minus n is equal to the conjugate of x with n. And vice versa. If you're building a real valued signal, then you need complex conjugate symmetric coefficients to reconstruct it. And what we've seen is that the real parts of the pairs of complex exponentials add, and the imaginary parts of these pairs of complex exponentials cancel. And that works for the Fourier series, complex Fourier series spectra, and it works for transfer functions as well. And that is it. So next time we'll be removing the time periodic assumption and looking to get onto the Fourier transform. Thank you.